Hello, everyone. Welcome to today's broadcast, an automated software solution for highly confident GC-MS compound ID. I'm Kaylin Chiarello-Ebner, the Managing Editor of Special Projects for LCGC, and I'll be your moderator for today's event. We are pleased to bring you this webcast presented by LCGC and sponsored by Cerno Bioscience. The MassWorks family of software products from Cerno Bioscience performs post-acquisition MS calibration, formula determination, and mixture quantitation on both low and high-resolution GC-MS or LC-MS instrumentation. It supports all major MS vendor data formats directly and works with all MS instruments, including GC-MS, LC-MS, time of flight, QTOF, and FT-MS. Cerno Bioscience products are used worldwide in major labs for pharmaceuticals, food, beverages, flavors, fragrances, natural products, environmental analysis, forensics, fine chemicals, and petrochemicals, as well as academic and educational institutions. We have a few important announcements before we begin. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit questions by typing them in the Q&A box, which can be found on the right-hand side of your screen. You can enlarge the slide window by clicking on the small square icon in the upper right-hand corner of the slide window, or by hovering your mouse over the lower right-hand corner and dragging the window to the desired size. The slides will advance automatically during the event. If you have any technical problems viewing or hearing this presentation, please click on the question mark help widget in the dock at the bottom of your presentation window. I'd now like to introduce today's speaker. We are pleased to be joined today by Don Keel, PhD. Don graduated from Ohio University in 1975 with a BS in chemistry, and in 1979 with a PhD in analytical chemistry. His career started at Bio-Rad Digilab, where he was the manager of the Applications Engineering Group, developing novel FTIR instrumentation and accessories. In 1986, Don co-founded Galactic Industries Corporation, which developed a universal software platform for analytical instrumentation. The platform sold over 50,000 copies worldwide. Galactic was acquired by Thermo Fisher Scientific in 2001. And since then, Don has been involved in several startup companies, including Cerno Bioscience, where he joined in 2004 as Vice President of Marketing and Product Development. Don currently holds 6 patents and has published or presented nearly 100 papers, articles, and talks in the fields of vibrational spectroscopy, mass spectrometry, chemometrics, data management, and data standards. Thanks so much for joining us today. Dr. Keel, please get us started.
Okay. Thanks very much, Kaylin, and thanks everybody for taking the time to attend this webcast today. As Kaylin mentioned, the title is An Automated Software Solution for Highly Confident GC-MS Compound ID. This is a brief outline of what we're going to cover today. I'll go through it quickly. We're going to discuss a little bit about GC-MS library search as it's used for compound ID and some of the limitations of the current technology. Importantly, we're going to also talk about what I call the coelution problem, which is the problem of identifying mixture peaks that are coeluting and not pure. And then we're going to move on to talk about how we can enhance GC-MS library identification using complementary and orthogonal metrics to improve the accuracy of the identification. We're going to then go through very briefly our method of how we attain high mass and what we call spectral accuracy on single quadrupole GC-MS instruments, which can be used for formula confirmation, which assists in the library search. We're also going to be talking about retention index matching. and retention index matching, I believe, is very powerful and somewhat underutilized metric. And if set up properly, it's actually quite easy to use and gives you very high confidence in helping to identify unknown compounds. And then finally, we're going to kind of work through the workflow of the software. A general overview. We'll look at some simple sample results on an agnostic sample of just simple VOCs. And then we'll go through a brief summary, and then we'll open it up for questions and answers. So GCMS, the current state. GCMS has been around for library search for qualitative analysis, been around for decades. It's actually really powerful. And over the years, the libraries have grown extensively. The quality of the libraries has improved. The instrumentation has improved. The sensitivity has improved, the throughput, the ease of use. But really, no really significant progress has been made to assist the analysts in determining the correct match from a long list of possible hits from a library search. And this can lead to sometimes tedious and time-consuming review by even an experienced analyst. It can lead to costly reanalysis and or unidentified or even misunidentified compounds. So let's talk a little bit about these limitations. First of all, when you do a library search on a particular peak, the hit lists, as we call them, are not always definitive. There's not like typically one answer that stands out way above all the rest. It's usually kind of a blend, and a lot of times it's left up to the operator to make some decisions, which many times he or she can by using chemical knowledge or knowing what the product is. But for true unknowns, that's not necessarily the case. The other problem, which is a big problem, is colluding chromatographic peaks. We don't always know that a peak is pure or not. And this can lead to poor library searches and or even quite misleading library matches. In the ideal situation, good analytical practice really dictates that we should use additional metrics or measurements. So back to where we were, this is just a simple example of a mass spec search of a mixture compound, which is located here at 2.57 minutes. It's not a pure component. It's actually a mixture peak. And so what happens is when we do the search, again, this is from the NIST library search, the match values, and I like that you can look at a number of different metrics in search. I like the match value. 1,000 is a perfect match. Anything in the 900s is a really, really good match. And what happens here, because we have a mixture peak, is that the match results are somewhat degraded. And it's not really clear what the correct match is because, again, it's a mixture. In actuality, the component is toluene because it's the major component. But still, we don't have a high degree of confidence when we do this library search.
Now, when we perform a search on a pure peak, we get a long list of excellent match values. Of course, the problem still is the answer to the question, what is the correct compound? Unfortunately, even in GCMS libraries, the fragmentation patterns can be very similar for similar compounds. In this case, the compounds are isomers of each other. This is one of the weaknesses of MS, the ability to discriminate between isomers. So, as I was saying, there's a number of approaches to addressing the coevolution problem mathematically. NIST has a program called AMDIS you may be familiar with, and some of the vendors have their own solutions as well. We use a slightly different method to try to identify and deconvolve co-eluding peaks into pure component spectra. And I'll just very briefly run through how this works without getting into too much detail. first of all, we do the peak picking on the run, and we just read the entire run into our software as it's generated by whatever GCMS instrument you may be using. And we locate all the chromatogram peaks, and then we run what we do is we evaluate each peak for its signal to noise, which produces statistically what is known as a t-value. We then look at all of the spectra across each peak and perform something called principal component analysis. This is a very common statistical method for determining the number of variables within a given data set. And the beauty of it is, what it tells us is it tells us the number of pure component spectra, or the number of colluting peaks within that one chromatogram peak. It's very sensitive, and it's a very robust approach. It's not a new approach, but it's used in statistics very commonly. And finally, we look at pure peaks, and we identify them with the highest t-value, and we use those as model peaks for analyzing the remaining mixture peaks and trying to unwind the peaks into their pure component peaks, and as well as their pure component spectra. Now, for complex GCMS runs, the pure component peaks aren't always available. So many times what we do is we'll use a standard run, which we'll talk about later in the presentation, to get pure component peaks to perform this methodology. And what you see here at the top is simply a tick. And then we have analyzed it. We've picked the peaks. We've analyzed it. We get the t-values, which are shown in the middle. That's just an indication of the quality of each peak. And then below is the results from the principal component analysis. And what that tells us is which peaks are pure, which peaks have 2 components, which peaks have 3 components or more. There's typically a realistic limit of about 3 to 4 components that you can satisfactorily unwind. That's just a limitation of the instrumentation signal to noise and the mathematics. And then finally, what we do is we actually use this model peak to do a fit, to try to understand the location and the intensity of the underlying pure peaks in the mixture. In addition, we look for a constant across the peak, which is really representative of an unchanging spectral background. Typically, it could be column bleed is very common. And this is really nice because it means the user doesn't have to do any manual background correction. It's done automatically. It comes out of the algorithm itself. And once the underlying peak positions and concentrations are known, we can then solve using, again, something called CLS, or classic least squares fit, to solve for the matrix of pure component spectra. Sounds fancy, but really what we're doing here is you see the top curve. That's the mixture curve, the red and the blue. The red represents the measured tick peak, and the blue is the fitted tick peak, which is composed of the 3 components shown as the black trace, the green trace, and the purple trace. So basically what we've done is we've solved for the underlying peak components that make up that chromatogram peak. Once we do this, we then can use our CLS method to back out the mixture peaks. So we've backed out the 3 spectra, which are representative of the 3 pure components that make up that colluting peak, and we can send those off to be analyzed using the NIST search and our other orthogonal metrics, which we're going to discuss. So let's talk about those other metrics that we can use. And the idea here is we're going to use other orthogonal metrics to improve the accuracy and the confidence of our unknown identification. Well, conventional wisdom as an analytical chemist, conventional wisdom dictates that to really truly identify an unknown, we should use multiple instrumental and/or chemical tests. For example, a classic analytical problem for elucidating the structure, you would use mass spec, NMR, potentially infrared, elemental analysis, and potentially some chemical tests. But in the real world, the problem is that mass spec is so much faster and so much more sensitive, and it has very robust chromatography interfaces. It is many times the single measurement choice, simply because the samples are complex and the time and the amount of sample required to make these other measurements is just overwhelming. So we tend to rely almost exclusively on the MS data itself to give us the answer. So the question is, can we do something with using just the GCMS data and the chromatography data to improve our confidence of our unknown identification? Well, one thing we can certainly do is we can go out and we can purchase a high-resolution accurate mass instrument. The beauty of these instruments is that you can use the accurate mass information to elucidate the formula identification of the unknown and validate it against the library. So formula ID validation is very powerful. Another advantage of high-resolution instruments is the technology in TOF and Orbitrap instruments. Typically, you get significantly better sensitivity, and that's something that you can't make up, and it's always going to be an advantage for these higher-performing instruments. And in addition, of course, there's higher resolving power, and higher resolving power is always better. It helps us, gives us the ability to unclutter the mixtures, for example. But it's at the cost of more expensive instrumentation, higher complexity, and of course, a more sophisticated user is usually required to run it. MSMS is also a very powerful tool. It can assist us to unravel true unknown IDs by performing more complex, however time-consuming experiments. So the question is, can we produce some of these complementary metrics on a conventional single quad GCMS? And the answer is yes. It can be done with no changes in hardware to your existing GCMS instrument. This is really nice because it turns out this can be a very cost-effective way to improve the confidence of your analysis of unknowns. It's quite easy to perform. It does require an additional step, which is that you need to perform a single calibration run, and we'll discuss this as we go along. Again, it's not going to be as sensitive or selective as a high-resolution GCMS instrument, but it's going to really improve our confidence in our ability to identify unknowns using a conventional single quad GCMS instrument. Okay, so let's talk a little bit about how this is done. It sounds like magic. How can we get unknown compound ID like you would in a high-resolution instrument on a single quad? And actually, this is an expertise that Cerno had developed over a decade ago, and it's actually commonly used on both GC and LCMS instrumentation. And let me go over briefly how it works. When we look at a typical mass spec on the instrument software, we typically see basically centroided data. In other words, the data has already been processed by the computer, and we represent the spectra as a series of sticks. And this is just an isotope profile of a compound measured with a quadrupole instrument. But in reality, what the instrument is actually doing is it's actually measuring a continuum, which looks something like this. And that curve, the width of those peaks is reflective of the resolution of that particular quadrupole instrument. And then what happens is the mass spec quadrupole instrument firmware will typically turn that into the Centroid data, which you're used to using. But in reality, if we look at a series of spectra, even at almost identical masses, you can see significant difference in the isotope patterns, which basically gives us a fingerprint to help us do formula identification. And this ability to accurately look and quantitate this isotope profile is what we will refer to as spectral accuracy. And we can use this information to help us identify unknowns with quadrupole instruments. So in a conventional mass spec instrument, what we do is we do a calibration or a tune, and primarily what the tune is doing is that it's basically taking a known compound of a known mass and making adjustments in the software such that the mass of the known compound lines up with what we measure. So effectively, we know in this case this is the actual spectrum that should be measured. The black is the measured spectrum, and the calibration usually involves simply shifting the values so that the masses line up. That's a traditional calibration. However, you'll notice that the isotope profiles of a calculated spectra and a measured spectra don't line up. That's the spectral accuracy. And the reason for this is because the line shape, or the line shapes measured in mass spectrometry, due to the inherent characteristics of the way that we measure ions, is undefined. So we take a bit of a different approach here. What we do is we measure our standard, and then we estimate the effective resolution of the instrument, and we choose a line shape of a known analytical function, which is about the same as what the instrument is measuring. The difference is that line is mathematically defined. It's known. We know its equation. It's typically Gaussian in nature, although it can be usually a blend of other types of line shapes, but we know it. We then look at the theoretical spectrum at infinite resolution, which is shown there in red, and we effectively convolve our chosen line shape with that to produce a spectrum of lower resolution, but it's well defined because we know exactly what its line shape is. Then what we can do is we compare this ideal spectrum to the measured spectrum, and through the magic of mathematics, we can actually calculate a correction function, which when applied to the calibration ion or to an unknown ion, can produce a spectrum that has not only accurate mass position, but also accurate known line shape positions. So here we're applying the function. That's a calibrated spectrum now, and that's the uncalibrated spectrum. So what we've done is we've calibrated both the mass position and the line shape. The beauty of this is that we can now take a conventional single quad GCMS, and the manufacturer may specify the mass accuracy to within a few tenths of a Dalton, and we can improve that by a factor of about 100. And we can get down to about 5 millidalton, or the third decimal place in mass accuracy. So that helps us utilize the single quadrupole instrument to make it into an instrument that's capable of doing formula identification. But that's still not really as good as the mass accuracy as you would get from a high resolution instrument. But the other thing that we get out of this algorithm is that we have this ability to match the isotope pattern with a theoretical isotope pattern to get something that we call spectral accuracy. And this is extremely important, this concept of spectral accuracy, because the isotope pattern is a fingerprint. And because we've calibrated that pattern, we can now compare it very accurately with measured data that's been calibrated to give us a very robust formula ID, even at a lower resolution. So that's how it all works. How do we apply that in our application here, where we're trying to enhance the library search value? What I have here is, this is actually typically what one would do for a true unknown on, say, a high resolution instrument, is you know what the actual mass accuracy of your instrument is. And with our approach on a quadrupole, that typical mass error window is about 20 millidaltons. And that's the width of the blue line that you see the arrow pointing to there. And if we do a formula search, that produces, within that mass window with the elements we choose, it produces about 12 compounds. Which is the correct compound? That's the question. And even at high resolution instruments, you typically don't get a unique answer. You'll typically get a list of potential compounds falling within that mass error window. In this case, we're using the spectral accuracy, and you can see the black line is overlaid very nicely with the measured data. The black is the theoretically calculated isotope pattern, and the red is the calibrated. And that gives that there, if you look at the highlighted yellow there in the last column, it says spectral accuracy of almost 99.5%. That's an extremely good match. And indeed, that is the correct compound. So now we have the ability to do formula ID on a single quad. And we can use this information to help validate our library search. And if you're interested, this work has been published. There's a very good article in Analytical Chemistry published back in 2010, which goes into how this works in the applications as well in great detail. So let's talk a little bit about another metric that we can use, that we have at our disposal, is retention index matching. Retention index matching is a very powerful metric, and I believe somewhat underutilized. It's very orthogonal, in other words, to the mass spec measurement. So that's one of the things that makes it so powerful. The interesting thing about retention time data is it's out there. There's tons of it out there. There's readily available retention index databases. For example, in the NIST library, about 2/3 of all the compounds in their databases have repeat retention index measurements for multiple different types of columns. So the data is out there and it is available. And again, as I noted, the metric is orthogonal. So it's a really good metric to validate our unknown. The other thing is that retention index information is really good for identifying isomers. And that's something mass spec is not very good at. And a lot of times, obviously, isomers are quite important, and that's usually something that can be very challenging to get the right compound, get the right isomer in a library search. It does require some additional measurements, and I say sometimes. If in some situations you can actually use internal standards that you're already using for other purposes to really calculate that data. So let's look at the workflow, and we'll see how this all kind of hangs together when we actually apply this to our unknown. The first thing that we do is we need to perform this calibration run. And the calibration run is typically designed to give us information so that we can calculate the retention index, but also so that we can do our spectral accuracy, mass accuracy calibration. And for that, we use the built-in PFTBA gas that's built into most vendor instruments. We also use the calibration standard to get the pure peak values that can help us deconvolve mixture peaks. So this is done by the software automatically. We read the data file as it's produced by the instrument. We'll go through and actually develop these calibrations for you automatically. this is a typical calibration run. It consists of a series of alkanes, which are used for retention index calibration, and also gives us our pure peak shapes, which can then be used to help us understand and evaluate which peaks are pure and which peaks are mixtures. At the end of the run, this little blip here is we turn on the PFTBA gas. And this can be done in a lot of the vendors' instruments as part of the method. And what it produces, if you look here in the lower right-hand corner, that's the spectrum blown up a little bit of the PFTBA tune gas. And it's a really nice calibration standard that has ions spread out across the mass range. And we automatically utilize this to build our calibration for accurate mass and high spectral accuracy. Okay, so the first thing that we do after we've done our calibration run is we go in and we analyze our unknown, and we need to identify the mixture peaks and deconvolve those mixture peaks into pure component spectra. What happens in the software is after the analysis of the run, it'll pop up a plot like this. This is just a tick, and it's very simple. The lines that are in light blue are peaks that are pure. The lines that are shaded in red are peaks that have 2 or more components. And as we discussed previously, we will deconvolve these mixture peaks into their 3 pure peaks. And the nice thing here is we also get the relative areas of those pure peaks. And we then back out the pure component spectra. So the mixture peak will be broken down into its 3 pure components peaks, which we can then send off to do the library search, as well as the spectral accurate mass and retention index calculations. So we first perform a conventional library search to produce a list of the compound candidates. Then what we do is we validate each library match using our accurate mass spectral accuracy formula ID. And then finally, we apply the retention index match to provide another additional orthogonal compound verification. One other interesting side note here is because we are calibrating these spectra to accurate mass, you can actually build an accurate mass library. So if you have a subset of libraries that you want to have enhanced capabilities with, you can actually go and build accurate mass library. Many of the programs that do library search will support accurate mass data. So we're back to our example here. And again, just to remind you, this is our peak at 257, which is a mixture search. And when we searched it against the NIST library, for example, with our conventional, just using the NIST algorithm, we noted that the match quality was degraded, and there was some degree of uncertainty as to the identification of the peak. When we run it through our process of peak deconvolution, as well as the accurate mass and retention index information, we get somewhat different looking report here. This is actually a high level report. You'll see in the top row here, the retention times for that mixture peak at 257. You notice that peak 30 and peak 31 are both listed at 257. That's because it is a mixture peak. If you look at the areas, you'll see that one peak is substantially, or one of the peak areas, it's a major component, is substantially larger than the minor component by about a factor of 7. And so that's indicated that the mixture is a 2-component mixture. And note that now that the NIST search results, and this is just for the top hit in the hit list, we'll look at the sub hits in the next slide, now jumps up from the 700s all the way up into the 900s. So we've deconvolved our spectra. We get much better search matches. And in addition, our spectral accuracy, and what we've done here is for each hit in the library list, we go and look for the molecular ion, and we do a spectral accuracy match on it, and 99% is very, very good. So we have a high degree of confidence that we have the correct formula as well as the correct compound from the NIST value. And in addition, the retention index fit is calculated, and the way we calculate it is we scale it to a value of 100, where 100 is a perfect retention index match. 96 is very high. So that's yet another match value that gives us a high degree of confidence. Let's dive into the first peek and look at the detailed match list. And this is the search list for the major component. And now you notice that the NIST search value is in the 900s as opposed to the 700s when it was a unresolved mixture. So we've improved that dramatically. So we have a much higher degree of confidence in the compound identification. I've searched the library with replicates, so all the hits at the top are obviously toluene, so that's the correct answer. And the spectral accuracy, of course, validates the formula C7H8 for all these compounds with a high degree of confidence, as well as the retention index value. So we have these additional metrics that really help us enhance the confidence in the match values. Finally, we'll look at the hit list for the minor component. Again, high NIST values because we've effectively purified the peak. We separated into its two pure peak. Very good spectral accuracy of almost 99%. And again, the retention time index fit. But if you look at the top two hits here, the NIST value is not that different. So which is the correct answer? Of course, the formulas are the same. That means that the spectral accuracy is going to be the same because we're analyzing for the same formula. But the interesting thing here is the retention index metric is the thing that allows us to identify, in this case, the correct isomer of this compound. That's something that's very difficult to do without using this orthogonal information. Let's look at the pure peak. Again, we'll go back to this. This is the conventional search that we did using the NIST search in this case. We get good match values, but still we have a number of choices to consider here because there's no significant break in the top few compounds here. And again, these are actual structural isomers of each other. And this is a challenge with mass spec. And again, what happens when we run it through our orthogonal metrics is we get a nice confirmation of the formula in these cases with a high spectral accuracy. But again, the thing that helps us differentiate the isomers here is the retention index information. The beauty here is that these metrics can really enhance your confidence of the data with really very little additional work that has to be done. So let's summarize here. GCMS search, it's a very powerful tool used for decades, but sometimes it's inconclusive or can even be incorrect, especially when we're dealing with impure peaks or components that are not even in the library. The mass spec spectral accuracy approach on a quadrupole can provide very powerful validation along with the library search results. And of course, as we've seen, retention index matching provides a highly orthogonal metric for ID. And we've tried to make this as easy to perform on your day-to-day runs as we possibly can. And so in general, substantial gains in confidence and hopefully a reduction in your analysis time can be done. And this is done automatically through the software using a single calibration run. In addition, even if the compound isn't in the library, I'm not going to go into much detail, but we can identify the formula of the fragments. And this is powerful information to help you get clues as to what the true unknown is, even if it's not in the library. I just wanted to say this is available in a commercially software product. which we call MassWorks RX GCID, or GCID for short. It can be used either manually, running one run at a time, or it can actually fully automatically process data as it's produced from your instrument. It has a review mode, which lets you rapidly go through those tables and spectra that we were looking at to save you time, and generate reports, which can be exported to either PDF or you can copy and paste them into Excel. It's all highly customizable, and it's quite quick and very easy to use. It just takes a few minutes to analyze fairly complex runs. And if you're interested, you can go to our website to find out some more detailed information. And with that, I'd like to hand this back off to our moderator, Kaylin, and we open it up for questions.
Excellent. Thank you so much for that informative presentation, Don. And before we get started on the question and answer session, I'd like to once again remind our audience how to submit questions. You can submit questions by typing them in the Q&A box, which can be found on the right-hand side of your presentation window. Okay, let's get to the first question.
Okay, let me...
Don, so the first question is, how often do I need to calibrate the instrument for RI and accurate mass?
Okay, the calibration, the modern GCMS instruments are really excellent instruments. They're very, very, very stable. They've been refined over the years, and actually there's been independent studies done using our calibration technology that shows that the instruments can be stable for days and even up to a week. But I don't necessarily recommend that. What we generally recommend to people for both the retention index calibration and the spectral calibration be done once a day. That's more than adequate.
Perfect. Thank you. Okay, here's an interesting question. I know that to have a good identification with mass work, you should look for the father ion. I often work with plant metabolites, and often the father peak is missed. How do you behave in such a situation?
Great question. Yeah, so the point here is that not every, in GCMS when you're using EI, not every compound has a parent ion or what we call molecular ion or father ion. So what we do is, when you do the library search and you get a match, for each match in the library search, what we do is we take the formula of the match, and then we go and do an evaluation to see if there's a significant amount of the molecular ion there. If there's not, we still calculate a spectral accuracy, but obviously it's not going to be very good. So we flag it to say that, hey, this particular compound in the library match, you shouldn't really trust the spectral accuracy. Now, the additional thing that we can do in the software is we can actually walk through the complete spectrum and try to get an identification of a number of the fragment ions. And we can report those back to you in terms of its mass and spectral accuracy. It doesn't give you the compound ID, but it will give you the some clues as to what the compound might be in your particular application, which is plant metabolism, which is quite challenging.
Excellent. Thanks, Don. Okay, let's get to the next question. And this you did cover, but I think it's important to revisit. Can you please summarize the complementary and orthogonal measurements that you utilize to improve compound identification confidence?
Okay, what we're doing is we're using three different things, if you think about it. First of all, we're flagging which peaks are mixtures. We're making an attempt to deconvolve them, because that can lead to misidentification. The metrics that we apply is, one, we can do a formula identification of the molecular ion to confirm the library match. And this is done using our calibration technology, which gives you both high mass accuracy and what we call spectral accuracy. So that gives you a formula validation. And then finally, we also automatically do the retention index calculation, and we use the retention index databases that are commercially available to validate this. And this is in my opinion, this is one of the most powerful metrics that you can use because it's truly orthogonal, and it really helps in cases where mass spec doesn't do so well. For example, in my samples there where we were looking at isomers. So it's formula identification of the library match, as well as the retention index, as well as the mixture identification.
Very good, thank you. Okay, let's move on to this next one. How many commercial GCMS data processing software systems so far can be integrated with MassWork?
As far as I know, most of the commercial ones can be integrated with, certainly with MassWorks. This is a new product that we have, this GCID product, and it can be it's vendor agnostic. We work with all the major GCMS manufacturers to assure compatibility, and the compatibility pretty much boils down to our ability to read the data files, or for them to automatically export the data files.
Perfect, okay. Here's an interesting question. Someone asks, I have a data set of about 500 GCMS samples. Could you provide a rough estimate for about how long it would take them to analyze that data with this software system?
Okay, well, first of all, I should reiterate that the data that's already been collected is likely to be Centroid data, and once you've Centroided the data, we can't reanalyze it. You really need to run the data in raw and profile mode, and I did see a question about that, so that's important. To actually analyze a set of 500 samples, depending on the complexity, let's say, for example, maybe there's 100 components in your runs. It would take it takes the software about 3 minutes to process a run. So that's 3 times 500. So it's going to be a while. But in general, you can set the software up to automatically process the data as it's produced. So it'll actually walk along with you and process data as it's produced, so you don't get into that backlog situation.
Excellent. So can the results be piped into LIMS?
Absolutely. You can. There's multiple ways that you can export the report data. There's also ways that you could actually put the raw data in, although most LIMS systems don't necessarily handle raw the actual instrumentation data. It's again, the reports can be exported in a variety of ways. It's highly customizable software, and if you're so inclined, there's actually Python, which is a very popular scientific programming language, interfaces that allow you to do very sophisticated automation or integration with LIMS.
Okay, thank you. So someone says, I'm concerned about how much responsibility in identifying a compound lies in the analyst's lap and not in the hands of a computer or AI. Do you have any comments about that?
Absolutely. I always look at the data. I don't trust the computer 100%. I think the point here is that, and the other problem is we all want jobs, okay? We don't want the computer to totally take away our jobs, and I don't think it's capable. The important thing here is you want to give the analyst as much information as possible to make a correct decision, or to minimize the time he needs to make a decision. And that's where these orthogonal metrics really benefit. It's basically an assistant. It's an assistant to the analyst to help him perform his job better.
Excellent. Thank you. Okay, our next question is 2 parts. Does MassWork do deconvolution? And if not, how can I work on MassWork with a deconvoluted spectra?
Okay, just to clarify here, we have two different products. One is our what we call our just straight MassWorks, which is a research product, and then we have something called MassWorks GCID, which is our automation product, which we just kind of walk through, which automatically processes an entire run. Traditionally, MassWorks will not do chromatogram deconvolution. You would have to use this other product to do that. It's an interesting idea, something that we could consider, but right now that's the way it's structured.
Perfect, thank you. I have another question, and if it's helpful to pull up a slide, I can assist you with that. Someone would like to know, why does the same molecule show up in the hit lists multiple times?
Okay, it depends on how you do your search. You can, typical in libraries for GCMS, they make, they actually do replicate measurements, because there's a significant variability in the spectra as they're measured, which has to do with the state of the instrument, the brand of the instrument, the source geometry, so on and so forth. So you don't have to do it that way. I like to look at all of the replicates. So what we're seeing there is we're seeing the replicate measurements showing up on the hit list. That's why we have the same compound listed multiple times. Some vendor software filters that from you and just, only shows you that one compound and will hide the replicates from you. It's just a matter of preference.
Okay, excellent. And here's the next question. What if the compound is not in the NIST library?
If the compound is not in the NIST library, likely what's going to happen is you're going to get a hit of the library hit of something that's probably reasonably related to what you're looking for, but it's going to be degraded. We're going to still perform the operation, so you may actually get a good formula identification based upon the library hit, but it won't be in the library. So that might be indicated by a good spectral accuracy value, but a degraded library search hit. Or if it's just not picked up at all, you're just going to get bad numbers everywhere. If that's the case, you really have to back up a little bit and start to do things like MSMS, or as I mentioned, we also have the capability to help you identify the fragment ions in the spectrum itself. But then you have to do your detective work and try to work back to what the actual compound identification is. So that's that problem we can help, but we're not going to give you an answer. And in actuality, nobody can give you that answer without doing all that additional work.
Wonderful. Thank you so much. And unfortunately, it looks like we're just about out of time. I'd like to thank the audience for attending and for participating in today's event. And I'd also like to thank our sponsor, Cerno Bioscience, for making today's educational webcast possible. You'll receive an email alerting you when this webcast will be available for replay. We invite you to forward that announcement to your colleagues who may have missed today's live event. Thanks to everyone for joining, and we'll see you next time. Goodbye.